Well, nice to see everybody. Hope you all had a nice weekend. So the plan for today is to begin work in chapter 2. So we're going to move on from first order differential equations and now start to take a look at second order differential equations. So these are going to be now differential equations that involve second derivatives. So systems where, or situations where not just the velocity is important, but maybe the acceleration also tells us something about the behavior over a long period of time. So just to kind of start with the most general case, this is in general what a second order, we're going to take a look at linear differential equations, second order linear differential equations. So now we have a second derivative, but the expression that we're multiplying each of the terms that have a y in it, right, only depends on the independent variable. So there are just some explanations of the dynamics of glass breaking and bridges and things like this, if you're kind of just curious about doing some research on your own about where these things come up. And we'll take a look at, in particular, some systems from physics when we look at applications of this with mass spring systems. So let's just kind of dial it back before we take a look at the most complicated cases. And let's consider, or what you guys looked at for the reading quiz was to consider some second order differential equations. And in particular, all of those didn't involve the first derivative at all, right? So here we have some equations that tell us, for example, the second derivative of a function x is equal to -1 times itself. And so from the reading, from the quiz, you should have convinced yourself that something like cosine of t works, or something like the sine of t works for these, because the first derivative gives us the other trig function, and then the second derivative gives us the original one back with the sign change. So when we have like a sign change in a second derivative, that should bring up notions of first, of sine and cosine. And this equation over here, hopefully you realize is exactly the same as the previous case that we looked at, just pulling the x to the other side. So initially over here, we're thinking about differential equations that look like x double prime plus some constant k times x is equal to 0. And what we can see over here is that when that value k is positive, we tend to be getting things like sines and cosines, because that's telling us the second derivative gives us a sign change in the function. And if we have something like this, which is a little bit different, so this would be equivalent to trying to solve this differential equation. For something like this is saying what's a function whose second derivative is exactly the same as the function itself. And so in those situations, hopefully you convinced yourself that exponential things make sense for those. And then over here, we kind of have one that's a little bit trickier, but we could rewrite this. Oops, excuse me. As x double prime is equal to -4x. And then kind of the idea here on the reading quiz is because we have this sign change with the second derivative, an exponential isn't going to make sense and a trig function makes sense. But when we have a coefficient here, just using the sine or the cosine wouldn't work because we don't get any multiples that come out. So trying one of these and then figuring out what the value of b is that's going to make this work, that's kind of the one way to approach that one. So in this case, we would get solution such as cosine of 2t or x is equal to the sine of 2t. So that's a quick recap of the videos and the quiz questions, but anything that you would like me to clarify relating to that?
So x can equal cosine and sine. Could they equal negative cosine and negative sine?
Yes, so we'll take a look at how we can get the most general solution. That's right. So these are a couple of solutions, but you should be expecting the most general solution should have some arbitrary constants in it. So we'll talk about how we can go from finding a couple of solutions to then how can we use those to generate the most general solution. So then, yes, we could have also have picked some multiple of that. So like x is equal to minus cosine of 2t, that would work also.
Um, I was gonna say, so we don't exactly know what it's going to be, right? It's just like these are the most likely options, correct? Okay.
Yep.
Because I was thinking with some of them, like couldn't there be a possibility where there's a negative sign in like the exponent?
Yeah, so that's right. Very good point. And in particular, this one over here, that would work for this one, right? Because if you took the first derivative, you get the negative that comes down. And then if you take the second derivative, you get a second negative that comes down. And so you see that actually the second derivative in that case gives us the same function back. So yeah, that's right. These two would be two possible solutions for that differential equation. Yep. Yep, Kyle, question?
Yes, it looks like in the readings, B is often used for trig functions, and then they have R for the exponential. Are you going to be sticking to that norm? Is that something that we normally do, or it was just part of the book?
So I'll just say that different books use different letters for different things. I think A and using B inside of there is going to make sense for where we're heading with this. Using R is pretty standard for the power of the exponential, but I'll just say, if someone uses K instead of R, it shouldn't affect things too much. Yeah. So maybe to answer your question is, there's actually not that much consensus on what letters are used for certain parameters, unfortunately. So I'll try and keep it similar to the textbook. There are some cases where there actually is some standard notation, like mu is used for an integrating factor, but this textbook uses R for the integrating factor, which is not very standard. So I kind of stuck to the standard notation for there. So I'll just say, like, if there is standard notation, I try and use it. If there isn't standard notation, then I'll try and use what the textbook uses. Okay, so any questions about now? So yeah, right now we're just trying to like read the differential equations, come up with some educated guesses about what the solutions might look like. This might be a little unnerving. So yes, we'll develop an algorithm, a more definitive way of finding these solutions that doesn't just involve guessing at random. But we're not guessing at random here. We're doing some educated guessing. Okay, any other questions? Okay, so now let's consider what happens when we have a differential equation like this. So now we're throwing in the first derivative as well as the second derivative. And so we'll be working with differential equations that look like this for this week. And what I mean by look like this we're going to take an even more simplified case where not only is the differential equation linear, but the things that are being multiplied to the dependent variable derivatives are just constants. And on the right side, we set it equal to 0, and we call this a homogeneous differential equation. So here, we're going to use constant coefficients. And we're going to consider at first only the homogeneous situation. Excuse me. And so again, by homogeneous, what we mean is we set the right side equal to 0. So the equation that we're looking at in 2 would be like a very general example of the types that we're going to take a look at. So let's take a look at this differential equation, and let's try and think about what we might expect the solution to look like. So this is a differential equation, which is saying we want the second derivative plus 10 times the first derivative plus 9 times the function to equal 0. So in other words, what you can think about is adding multiples so is there some function x that when I add these special multiples of itself, its first, its second derivative, that everything perfectly balances and cancels out. So let's think about the types of solutions we've been considering and see whether they might be good candidates here. Okay, so let's say, for example, let's start with the last one I just wrote. I want to see whether a solution like x is equal to sine of b of t. If I plug that into the differential equation, would I get 0? Is there some value of b that might work here? Feel free to chat in if anyone has a thought on this or speak in. Let's see, I think so. What happens if I take the derivative of sine? What type of function am I going to get back?
So I guess just going left to right, you'd have negative sine plus 10 cosine plus 9 sine.
Yeah.
Which
Yeah,
I think
so
equals
I
the
think
same.
without going too crazy, this is exactly what I was trying to hint at, right? Without even plugging it in too precisely, we can see that if x is sine of b of t, then that would go over here. The derivative of this would be a cosine. That goes in here. And then the second derivative of this would give me another sine back. So it's possible that I have a sine here and I have a sine over here, but in the middle I would have a cosine, right? And so there's not going to be a nice way for these sine terms to cancel out this cosine term. At least very clearly, it's not clear to me how that's going to work. And we can have a similar argument for why the cosine might not be the most logical choice from the get-go, because if I take the cosine and plug it in, the derivative is going to have some sine term that I won't be able to cancel out somehow with the other terms. So it makes sense that e to the RT, that seems possible here, because every time I take a derivative of e to the RT, I get back another exponential that has the same power, right? I get back a multiple of this. So it makes sense that if I take first, second, and zeroth derivatives of this and add them together, they're all going to be multiples of e to the RT. And so if I pick the right value for r, that's going to cause all of these things to cancel out just so. Does anyone know what have one possible solution for this one?
I'm thinking e to the negative t.
Yep. How'd you get that one? Is that Abraham?
Yeah, well, I plugged it in, and I realized it needs to be negative, because if it's not negative, the 10 would it'd all be positive. So we need a negative in there to make it negative.
Okay, cool. Thank you. That makes total sense, at least to me. So if we're going to add these up, if we pick the positive power here, if we have a positive value for r, then we'd just be adding a bunch of positive things together, which couldn't cancel out. That explains why we might want to think about using a negative sign here, since the first derivative would absorb that negative sign, the second derivative would become positive again, and then these things could cancel out as long as you pick the right value. So this checks out, and I'll leave it to you to verify, but right, the first derivative would be this, and then the second derivative gives us back e to the minus t. And so now if you take this plus 10 times that plus 9 times that, everything cancels out just so. Any questions? Okay, so now this is getting at what some have been asking. So here is a solution. Again, what we would like to ultimately find is like, what is the most general solution to this differential equation? So this is just one specific solution, but it doesn't describe what all of the solutions might look like. So one thing to note here is we should expect some arbitrary constant in our solution. And so what we see is x is equal to e to the minus t is a solution. To that differential equation. So let's try a different solution. Let's see, well, if I were to multiply that solution by some arbitrary constant, no matter what that constant is, hopefully you can see that when we take derivatives, the c, just gets pulled out. So it's almost like every one of these first, second derivatives that we take is just c times what we had above here. So when I add these all together, I take x double prime plus 10 times x prime plus 9 times x. And simplify, we could just factor out the c from all of those terms. And we can see, okay, that also checks out. So this tells us that this is a solution as well. And that looks a little bit more general than the solution we proposed at first over here. So yeah, we can see that if e to the minus t works, any constant times e to the minus t works. And that's ultimately what we want to do, is describe what would the most general solution look like. Any questions? Okay, so this is true in general. So if we have
So C was the most general solution? Sorry.
so far, yes, it is not the general solution just yet. We haven't described all of the possible solutions, but we're heading in that direction. So just to kind of summarize this general fact, that is, if we're working with a differential equation that looks like this, okay, and it's really important that we have a 0 on the right side. If we don't have that 0, this is not necessarily going to be the case. But if x is a solution, then multiplying that solution by a constant is also going to be a solution. That worked for the example that we're thinking about right now. That works in general. Okay, so we are working with this, and so far we've got this as a possible solution. But again, yes, the question is that all of them? And the answer is this is not done yet. Did anyone find another solution to this that wouldn't fall into this sort of template that we have so far? Okay, so here's my suggestion. So let's go with the assumption that our solution is going to look something like this. And really what we're asking is for what values of R is e to the RT going to be a solution? And we've solved problems like this already, right? We had some of these, I think, on the first homework maybe. So what can I do to figure out what values of R are gonna guarantee that e to the RT is a solution? What does it mean to be a solution to a differential equation? Any suggestions?
I set it up as a quadratic using the coefficients as R. I don't know if that's correct though.
That is correct, but it might not be clear why. So let's try and maybe just illustrate why that's true. So how do we check to see whether something is a solution?
Plug it in to the differential equation by taking the derivatives of e to the RT.
Yep, let's take the derivatives and then we're going to plug it in to the differential equation over here. That's right. So we've got the first derivative, R would come down. We take the second derivative using the chain rule, another power of R comes down. And so now when I plug each of these into their corresponding place in the differential equation, we've got x double prime is R squared e to the RT plus 10 times x prime, which was R e to the RT, plus 9 times e to the RT is equal to 0. So now we want to find what values of R are going to make the left side 0 for every single value of t. And so what we can do is factor out in e to the RT from each of these terms up here. And what's left is R squared plus 10R plus 9. And that should equal 0. And this, we can factor, for example, into R plus 1 and R plus 9. So what this analysis tells me, and we're kind of leading down to the next part, is that if I have something like e to the minus t, meaning if R is equal to minus 1, then we get one solution. And from this factor, we can see that if R is equal to minus 9, then the left side would indeed give me 0. So if I have something like e to the minus 9t, that also would work as a solution. So in 4, the part above, it's really asking us, well, is there another type of solution that you can find? Yeah. There's another one, e to the minus 9t. So we've got one solution, which we described before, that e to the minus t. And then we have a second solution now, which, well, if we know e to the minus 9t is a solution using this idea up here, then we know multiplying it by some constant isn't going to change the fact that it also would be a solution. And one thing that I'm going to ask you to verify on the homework that's due next week is that if I have two solutions, then the sum of those solutions is definitely going to be a solution as well. So you can verify this on the homework. I won't go through it now. But once I've got one general solution and a second general solution, then the sum of those two is going to give me the most general of all solutions. So notice here that our general solution has two constants. Okay, and that's because we have a second order differential equation now. So the number of constants that you have in your solution should be the same as the order of the differential equation. Okay, any questions?
You said the order of the equation will determine how many constants. Is that always?
Yep. So if you had like a third order differential equation, you'll have 3 and so on. Yep. Okay. Yes, so kind of I think interesting thing to observe here is that really what we could have said was, okay, I expect that my solution is exponential. So I know that my solution in the end is likely to look something like this. And really what we need to do is say, well, what are the values of R1 and R2 that we need in our solution? That's like what we have down here. And so to find these values, we need to set up and solve a corresponding quadratic equation. And notice that this quadratic equation has coefficients that came right from the differential equation that we had over here. So I had a differential equation x double prime plus 10x prime plus 9x, and that gave me that the corresponding quadratic that I needed to solve was 1 times r squared plus 10 times r plus 9. So we're going to get the coefficients of a quadratic equation that we need to solve from the coefficients in the differential equation. So one thing to note about what we're going to do today when we kind of lock in this process is solving these differential equations doesn't involve integration at all. It's solving quadratic equations. So it's actually quite a bit easier than what we were doing with integrating factors. There's actually no integration involved in this process. So let's kind of map out the steps here so we've got a general process. So I've got a differential equation. Here is the example that we just solved. We wouldn't, in practice, just go through it by randomly guessing things. We would go through it by saying, I know that my solution is going to look like this. I just need to figure out what R1 and R2 are. And if I were to try and plug something like this into this differential equation, ultimately what I'm going to find is those values of R are going to be the same values of R that satisfy this quadratic equation.
Can you say that one more time, Professor?
Yeah, so in order to figure out what the values of r that would work in the powers of the exponents, we're going to take this differential equation and set up its corresponding quadratic equation below. So the coefficient in front of the second derivative, that becomes the coefficient in front of the quadratic term. And the coefficient in front of the first derivative becomes the coefficient in front of the linear term. And then the coefficient in front of the constant, or in front of the zeroth derivative, becomes the constant term in the quadratic. So this works in general if we had a differential equation that looks like this, then the corresponding quadratic equation is going to be AR squared plus BR, plus C is 0. So we get the coefficients of the quadratic equation from the coefficients in the differential equation.
When we're solving these, can we jump to this step immediately?
Yep, I would highly encourage that, yes.
Okay.
Yep, and this equation has a name. It's called the characteristic polynomial or equation corresponding to that differential equation. So kind of step one is just say, write out the characteristic equation, polynomial. And for those, have you seen this used in another setting, characteristic polynomial? Sound familiar at all?
If you have like x to the fourth and x squared, you could like turn into quadratic formula with that.
I mean, if you had higher powers of derivatives. So if you have higher power, if you have a higher order differential equation, as long as it has constant coefficients, something like this could be applied. We'll see that later. That's one of the sections in this chapter. Yeah, so you can apply this to higher order differential equations. But if anyone's heard this term before, you might have heard of this in linear algebra. Maybe you're taking it now, in particular when you're finding eigenvalues of a matrix. And when we take a look at systems of differential equations, we're going to take a linear algebra approach to that using eigenvalues. So you'll see some linear algebra spill over into this, and we'll see why this is actually the same characteristic equation that you might have seen in linear algebra. But that's not important for now. What's important is, yes, I would just take this differential equation and then read off each of the coefficients. And then that sets up my quadratic equation. Okay, we solve the quadratic equation either by factoring, completing the square, quadratic formula, all of those methods. And on this one, we could factor into r plus 1, r plus 9 is equal to 0. So here we have two roots of this, -1 and -9. So that means that these would both work as solutions, and therefore any linear combination of those is also going to give us a solution. And down here would be our general solution. So that's it. I would say that these tend to be actually some of the easiest differential equations that we can solve because it's an algebra problem. You could do this in high school once you learn how to solve quadratic equations. Any questions?
If we determine that it's an imaginary root, what do we do in that case?
Yeah, good question. Yeah, and so you're getting a little bit ahead of things. But yeah, when you have quadratic equations, like you could have two distinct real roots like this. It's possible you have one repeated real root. What do we do when that happens? What do we do when we have complex roots, which also could happen? That's right. And we'll handle each of those cases in time. So what happens when we have complex solutions is exactly what we'll talk about on Wednesday. Yeah, so for now, we're gonna just be sticking to situations where these characteristic equations have real solutions. But yes, definitely you should be suspicious about, well, what happens when we don't have real solutions? That's when the cosines and the sines are gonna come back into the picture. So when we have real solutions to the characteristic equation, that's when we get exponential solutions. Okay, any questions? So I want to go through maybe one example together, talk about what happens when we have a repeated root, and then give us the rest of the time to just practice solving some of these at the end. So I'll go through this one together, just so if you're curious, like what is the work that we would need to show to solve something like this. So if we're looking at number 7, we've got second derivative of x plus the first derivative of x minus 6x is equal to 0. So what do you think would be a good first step here? If you want to do it, if you were doing it.
Identify the coefficients.
Yeah, set up the characteristic polynomial. Yep, thanks for sending in your chats as well. Yeah, so we don't need to explain where this comes from or why, but let's set up the characteristic polynomial, right, which in this case would be r squared, since we have a 1 in front of the second derivative. The coefficient in front of the first derivative is 1, so we have an r there. And then we have a minus 6 over here. Okay, then we solve that. That's going to involve factoring or quadratic formula. So here we would get r plus 3 times r minus 2 is equal to 0. So we've got a solution of minus 3 for r and 2. And then we can write out the general solution. Right, which in general is just going to be some multiples of each of the solutions added to each other.
So once we find ours with the work for this class, can we immediately write the general
Yep.
solution?
Mm-hmm. Yeah, and so really all the first couple sections of this chapter are going to be find the roots of some quadratic equation, and then you just need to know how those roots tell us something about this solution. Yep. Okay, any questions? So it's set up quadratic, solve the quadratic, and then you've got your solution to the differential equation. But I do think it is important for you to just know where this quadratic equation comes from. So this could be something that you're asked to do on the exam. I think this was something that you actually had to do on the, oh no, that is not something I asked on the reading quiz. But yeah, just be sure that this quadratic equation is not some mystical thing, but you're aware where it comes from, and it just comes from knowing a guess for what the solution might look like and plugging that guess into the differential equation. Okay, so let's take a look at question 8, unless there's any questions. I don't think so. So in question 8, we've got this differential equation over here. And we're told that let's give this a shot as a possible solution. Okay, and this looks different than the equation, than the solutions that we've been looking at, because in particular, this has a t right there, right, that the others don't have. So to check that this is a solution, I'll leave that for you guys to complete, but just be aware that when I take the first and second derivatives, right, what I would want to do would be find the first and second derivatives and then plug them into the equation, that when I take the derivative of this, we need to use the product rule because we have a product of two things. So it would be like the derivative of c times t times e to the 2t right? So when you have that extra t in there, it just makes the derivative a little bit more complicated because you have a product. But you would get c times e to the 2t plus 2c t e to the 2t. And when you write out this derivative, you don't want to just say that, okay, I can just call that constant c, because what we have here is that the constant in front of the first term should be half as much as the constant in front of the next term. So you want to leave these c's alone down here. And then I'll just say, you can take the second derivative of this, and it would be good just to verify that that this does indeed check out. And so what do you think is different about this differential equation that gave us a different looking solution?
The coefficient isn't constant. It has a variable in it.
So in the solution, yes, we've got t over here. So it's different than the types of solutions that we saw back here. So what is it about this equation, do you think, that's giving us a different looking solution over here?
The negative sign on the linear portion of it.
So we have a negative sign over here. That's right. That in itself won't always cause this difference. So let's kind of just step back. If we didn't know what the solution looks like and we wanted to find it, first thing we would do would be set up the characteristic polynomial, right? And then we would solve that characteristic equation. And what are the solutions to this differential equation, or this quadratic equation?
Is it 2 and negative 2?
It is not 2 and minus 2. The solutions should have the same sign because we have a plus sign over here.
Is it going to be different because under the square root, when you do the quadratic, they cancel each other out?
So what does that tell us about the solutions to this quadratic equation? Okay, yes, thank you. Someone mentioned that we don't have two distinct roots here, right? We have one repeated real root. So in other words, this quadratic equation, whatever it looks like, it is doing something like this. So the vertex is sitting right here, and we have a double root. If you factored this, you would factor it into r minus 2 squared is 0. So we have a repeated real root here. Which is r is equal to 2. And so we don't have an r1 and an r2. And so let me just say, as a special case, if the characteristic equation has a repeated root, then the general solution would look like C1 e to the R1t. And then for the second one, we have we put this extra t right here for the next term. So so far it's, we find the characteristic equation, we find the roots of the characteristic equation. If the equation has two distinct real roots, then we know we've got C1 e to the R1t plus C2 e to the R2t. If instead we have one repeated real root, then we get a solution that looks like this. In general, meaning two distinct roots, then the form looks a little bit different. So once you get the roots of the characteristic equation, then you need to know, well, do I use the general case or is this the special case when we have a repeated root? Okay, any questions? Okay, so if not, there's 10, 11, 12, 13, we've got 4 problems on this worksheet. And the last 2 are actually solving initial value problems. So one thing to note, when we're working with initial value problems for second order differential equations, here you have 2 bits of information. So we're not just given the initial position, but we're given the initial position and the initial velocity. So when you're finding solutions to initial value problems, it's the same idea. Just in this process, there's going to be 2 constants that you're going to need to solve for, C1 and C2. So don't worry about those initial conditions until after you've found the characteristic equation and found what the general solution looks like.
So on that number 8, just a clarifying question.
Yep.
The general solution would be C1 times e to the R1t plus C2 t e to the R1t. That one right there. One of those things will solve the equation. Like if I plug in x equals C1 e to the R1t or C2 t e to the RT, both of those things will solve it, basically. Yep. Is that okay?
That's right. Yeah, we didn't do all of the work up here, but yes, if you checked this one and plugged it in, that works. And if you don't have the t there as well, if you just had c times e to the 2t, that would work also. Yeah. So to just wrap up this one, since we didn't state the solution, the general solution to this one would look like, well, since we found one repeated real root, we would have c1 e to the 2t plus c2 t e to the 2t. So that's what this general solution would look like.
And then each of those terms would be solvable for the differential equation.
Each of those terms individually would be a solution, that's right, as well as the sum of those two. So the sum of those two things would be the most general solution. Yeah.
Yeah, but the individual parts are are a solution, not the solution, a
Yep.
solution.
Yep, that's right. Okay, so let's get to work on some of these. So I will split you up into breakout rooms and please help each other out. So
I guess I can go ahead.
Okay,
So
thank you.
first we subtracted the z to make it homogeneous, and then you can set up the characteristic equation.
Okay, yeah, so just one editorial comment there, that's right, is that you might have to do some rearranging of terms to put it into this like standard form before you set up the characteristic polynomial. Okay, great. Okay, then we've got our characteristic equation, yep, which was what?
I mean, I just converted it to x since it's just visually, but I just put x squared plus x minus 1 equals 0.
Mm-hmm.
And then we couldn't like factor this
Mm-hmm.
in our head easily, so we did quadratic equation.
Reasonable. Okay.
And then should I just tell you the factors that we got, or should I like plug everything in?
No, you can. I'll just write it out over here. So when you did this, then what did you get as the factors?
-1 plus or minus the root of 5 all over 2.
Okay. Any questions about that? Yeah, I think point here is, yeah, these don't always factor, so you might have to use the quadratic formula, and then even when you do that, we can still make sense out of these roots. So then what was the general solution here, Shamik?
C1 e to the -1 plus root 5 over 2 t plus C2 times e to the -1 minus root 5 over 2 times t.
Yep. Looks good. Any questions about that? Yeah, so sometimes we don't get pretty answers, but that doesn't mean we can still use this formula to write a solution which is not so pretty. But that's right, that works over here. Okay, thank you, Shem. Okay, on number 11, does anyone want to try this one?
Yeah.
Okay, Cortez, thank you. Go ahead.
So I just started out by factoring out 3 from everything, the left side,
Okay.
to get w prime plus 6w, or w double prime plus 6w prime plus 9w 0. Then from there, it's just factors are going to be 3 plus 3, w plus 3, I guess.
Sorry, I think I lost you. Chopped out for a second, Cortez. So then what?
So there, I pretty much just easily factored it out. I forget what the hell the thing is called, but I got w plus 3 times w plus 3.
Okay, so one thing I might suggest is you don't need to use R over here, but I wouldn't use W because W is holding the spot for the dependent variable. So yeah, you just want to think about this gives me some corresponding characteristic equation, and those roots are going to tell me something about the solution. Yeah, so when you're showing your work to me, yeah, please don't use the same letters because that's going to be a little bit confusing. Yeah, but you've got the right idea. That's right. And so now this factors into, what were the 2 factors that you got, Cortez?
Plus 3 for both of them.
Plus 3 for both of them. That's right. So we have a repeated root here. So in other words, this is this quadratic equation can be written as 3 times r plus 3 squared. So we have 1 repeated real root, which is should say -3, right? Because if the factors are +3, right, then we've got a -3. So what did you do with this root then to get the general solution?
Pretty much plugged them into the whatever equation we have
Okay.
for that, which is C1 e to the -3t
Mhm.
plus C2 times t e to the -3t.
Perfect. Thank you. Any questions about that? Yeah, and so here, because we have this repeated real root, that's why we have this t in that term. Any questions, or anybody do it in a different way and you're curious if what you did is okay? Okay, then how about number 12? Did anyone get through that one?
I was able to get a general form, but I didn't know how to like
Okay.
use the additional condition.
Sounds good. So what did you get for the general solution here?
I got W equals C1 e to the R1t. Oh, I mean 4t, and then plus C2 t e to the 4t.
Okay, I think over here you might want to have, so the characteristic equation is r squared plus 8r plus 16 is 0. And so when you factor this, how did that factor?
I got R plus 4 squared.
Okay, and so if you have a r plus 4 as
Oh,
a,
minus. Yeah, minus 4.
that's right. So we have one repeated real root of -4. So we're going to have a similar looking solution as we had in the previous one. We're going to have C1 e to the -4t plus C2 e to the minus, no, that's not exact, plus C2 times t e to the -4t. So here's kind of our general solution using the characteristic equation and the fact that we have, again, one repeated real root. So let me just stop there before we deal with the initial conditions to give anybody a chance if you want to ask about that. Okay, so then once you have the general solution, in this case, right, we can plug in 0 and we can first use this initial condition to say, okay, if I plug 0 into the general solution, I'm going to get C1 times e to the 0 plus C2 times 0 e to the 0, and that all should equal -2. So when I plug 0 into the second term over here, right, this all cancels out. And so I've got C1 times 1 is equal to -2. So this one would give us that C1 is actually equal to -2. And so now we can plug in that information, namely that I know that the constant C1 should be -2. And then to find what constant C2 is, I then would need to use this condition over here. So I need to find first the formula for the derivative of W. So that would be the formula for the derivative. And notice on this term over here, we had to use the product rule. And that's what gave us those two terms. And then we would plug in this initial condition that at time 0, the derivative would be 8 plus C2 minus 0, that all should equal 12. So that gives a C2 value of 4, solving for C2. So the general solution here, excuse me, the solution to the initial value problem here would be, we found that C1 was minus 2, and we found that C2 was 4. So we would plug those values back into the general solution and get our initial value solution. Any questions? I will, we're out of time, so I'll stop here. If you want to stick around and do 13, I'll stay on Zoom since I'll record this and put it up for those that want to take a look at it later. You're welcome to stick around. If you've already done it and you're kind of curious about whether your answer is right or wrong, I could quickly tell you that the solution here, and I'll record this on Zoom in a moment, would be 10 over 7e to the minus 5t plus 46 over 7e to the 2t. If you got this, that's great. If you got something close to it and you're not quite sure why it's off, I'll walk through this now. But I'll just stop so you guys can go if you've got somewhere else to go. So thanks everyone for a nice class. Good to see you all. For no homework due this evening, but there's a quiz due before Wednesday's class. And if you're curious about walking through 13 or any other questions, just stick around. Thanks.
Could you scroll up a little bit? Thank you.
Yep.
All right, could I also ask you a question about number 8 really quickly? Was it 8? Hold on, no, not number 8, number 10. So when we subtracted by z to get the homogeneous equation, on something like an exam, do you want to see that step, or can we just skip it in the name of finishing the problem in time or time pressure and just move on?
I mean, I think that the more work that you show, it's better for you in the long run, more so than it is for us. So, you know, we grade things with partial credit. So the more work we see, like the easier it's going to be for us to give you partial credit. So for a step like that, you don't have to show it, but like if we see that you actually did that process of bringing the z over, and then we see your characteristic equation, and if for some reason you did a stupid mistake when you set up your characteristic equation, you would still get credit for knowing that you had to bring that z over. Whereas if you just write an incorrect characteristic equation without showing any intermediate step, it's not clear to us, like, okay, did they do that step and just make a careless mistake? Or is this student not really understanding what the characteristic equation is? And so like the less work that's shown, the harder it is for us to get inside of your head and get into your thinking and then assess like how much credit you deserve for that thinking. So
Okay,
I would say a step like that doesn't take too much time to write out, and I think it's useful for yourself and for the grader just to include that. Like you don't have to, but I think it's best for you to show that step.
Okay, thank you.
Adam, I had a question
Yeah.
about 12.
Sure.
So for W prime in the red there, why did you split up C2t e to the negative 4t?
So you've got a product for this one. So when you're taking the derivative of this term, you need to use the product rule.
Gotcha. Okay.
Which says we're going to take the derivative of this times this, and then add to it this times the derivative of that. So yeah, one of these, this came from that term, and this comes from, well, this comes from that term over there.
Okay, cool. Got it.
Okay,
Thank you.
so for those that are around, do you guys want to go through 13? Or were there other questions? I'm happy to answer whatever questions you have, and then I can record 13 for Zoom. Or is there anything else? Okay, well then we'll go through this. Cortez, can I erase the stuff in 13?
Yeah, you're good. Thank you.
Just so I have some space here. Okay, so let's pretend we don't know what the answer is. And so if we were working with 13, same sort of idea in that step 1 is let's set up the characteristic equation. So we would have r squared plus 3r minus 10 is 0. And again, we're just getting the 1 comes from the 1 in front of here, the 3 from the 3 minus 10 gives us the minus 10. And then we find the roots of this. And this one we can factor into r plus 5 and r minus 2. So we get 2 distinct real roots to the characteristic equation. So that means we don't have the repeated root formula. We just use the y is equal to c1e to the minus 5t plus c2e to the 2t. Any questions? Okay, so then this one actually becomes a little bit trickier than the previous one. Maybe there's less calculus involved, but a little bit more algebra involved in finding the values for the coefficients from the initial condition. So here, I can plug in the initial condition of y of 0 is equals 8. And so if I plug that into our general solution down here, we would say y of 0 is c1 times 1 plus c2 times 1 is equal to 8. So when I plug in the initial position, I don't know what c1 or what c2 are. I just know what, I know some condition that c1 and c2 need to satisfy. So I'm trying to solve for 2 things, C1 and C2, so it makes sense that we're going to need 2 bits of information to solve for 2 unknowns. So using the position, we've got 1 piece of information, and then we can use this initial velocity to take the derivative of our general solution. So I want to take our general solution, take its derivative, and then plug the initial velocity into that formula. So here we would get minus 5c1 plus 2c2, and all of that, we're told, should give us an initial velocity of 6. And so what we have left is 2 equations and 2 unknowns. Namely C1 plus C2, that should give me 8. And then from the derivative, we know that minus 5C1 plus 2C2, that should give us 6. And then solving this using whatever methods you like, I got that the value for C1 was 10/7, and the value for C2 was 46/7. So the particular solution, therefore, is 10 sevenths times e to the minus 5t plus 46 sevenths times e to the 2t. And so I didn't go through the details of the algebra in solving those two equations, but let me know if you have any questions about that. All right, any questions?
Nope, I'm all good.
Okay. Awesome. Well, then have a good day, and I'll see you on Wednesday.
Thank you.
See you.